let's start talking about some examples. First, let's just talk about two functions here, m and n. These are both functions of x and y. Let's say m is 3x squared plus 2xy, and n is 3y squared plus x squared. As will be true for most examples we'll deal with, you can see immediately that both m and n and any of their partial derivatives will all be polynomials in two variables, so they'll be continuous everywhere in the plane. So we don't have to worry in most circumstances about the hypotheses for the theorem we talked about, which tells us when there's some function c of xy, which has c sub x equals m and c sub y equals n. What is the statement about when such a function c exists? Well, such a function c will exist if and only if, remember this is under the niceness conditions, which are clearly satisfied, such a function c will exist if and only if m sub y equals n sub x. Well, here it's easy to compute that m sub y is 2x, n sub x is 2x. They're equal. So what does that tell us? That tells us that the function c must exist. Of course, it doesn't tell us how to find it. So what we're going to do now is talk about how we can find such a function c. And luckily, this isn't just some abstract existence theorem, or technically the theorem is just an abstract existence theorem, but there is a way, an algorithm that will allow us to produce such a function c. And really, it's a very straightforward algorithm. We want to find c here with c sub x equal 2x. I'm sorry, c sub x has to be 3x squared plus 2xy, and c sub y equals 3y squared plus x squared. We can start with either one of these equations. Just as a habit, I start with the one involving the partial with respect to x, but everything will work out just the same if you start with the other one. So let's start with this first equation. We ask, if we need a function c whose partial with respect to x is this function, 3x squared plus 2xy, what does c have to be? Well, c of xy is just what you get when you integrate this with respect to x. The first term when you integrate with respect to x is just x cubed. The second term when you integrate just with respect to x, holding y constant, is just x squared y. Of course, this isn't the only function whose partial derivative with respect to x is 3x squared plus 2xy. I could add an arbitrary constant and I'd get the same partial with respect to x, but here's the key thing. It's not just an arbitrary constant that I could add. I could add any function of the variable y. I'll call that g of y. This is any function of just one variable, the variable y. Because when I take the partial of c with respect to x, I'll get exactly 3x squared from this term. I'll get 2xy from this term. And the partial of this with respect to x will be 0 no matter what function of y I put here. So from that first equation, I determined c has to look like this. Well, for this c, we now compute the partial with respect to y. That's just using the formula we just produced. The partial with respect to y of x cubed is 0. The partial with respect to y here gives us x squared. The partial with respect to y of g of y is just exactly g prime of y. So the partial derivative of this whole thing with respect to y is x squared plus g prime of y, and we need that to equal 3y squared plus x squared in order for this second equation to be true. Well, that tells us immediately g prime of y is 3y squared. So g of y equals y cubed works. Of course, we could add an arbitrary constant to this as well. We could use y cubed plus 7. Right now, all we need is some function c that works. So we'll just take y cubed as a representative of something which works. So when we put that all together, we get c of y is, what is it, x squared plus x squared y plus y cubed. And then you can just check yourself probably in your head that that's not c of y, that's c of xy. C of xy is x squared plus x squared y plus y cubed. You can check that that function c really has c sub x equals m here, and c sub y equals n. What does that tell us? That tells us we can now solve this differential equation. This was exactly our m, and this was exactly our n from before. Because this is c sub x, and this is c sub y, the solution to this equation can be found by just integrating both sides. And the integral of the left side is exactly c of xy. Here you have the c sub x, and here you have c sub y, y prime, which is c sub y dy dx. And of course, now there's an arbitrary constant on both sides. When you integrate, we'll put those on the right, and you get c sub xy equals a constant c. Putting in what we computed above, c to b, we get x cubed plus x squared y plus y cubed equals c. Again, this is the general, though implicit, solution to the differential equation. And as always, you should check your work real carefully, which basically means nothing more than use implicit differentiation here on both sides. Use implicit differentiation. When you take the partial of this with respect to x, you'll get exactly 3x squared plus 2xy plus x squared y prime, which is that term, plus 3y squared y prime, which is that term, equals 0. You get exactly the original differential equation. Let's look at a totally different differential equation. Here it's written in differential form, and ask, can we solve y over x plus 6x dx plus log x minus 2 dy equals 0? Notice that since we have log x here, for this whole problem, we insist x is greater than 0. Otherwise, none of this will make sense. Certainly, the y over x won't make sense when x equals 0, and the log x won't either, and we need x bigger than 0 for this part to make sense. So, is this something we can solve? Well, again, if I call this m and this n, then we can check m sub y is exactly 1 over x, and n sub x is exactly 1 over x. Notice that they're the same. So I'll just put a check here. That means there will exist a function c of xy with c sub x equals m and c sub y equals n. Can we find it? Yes, we do the exact same thing as we did in the previous example. We need c sub x to equal y over x plus 6x. So integrating with respect to x, we get here y times log x. Remember, we don't need log of the absolute value of x because x will be greater than 0 here. We get y log x plus 3x squared. So this will be, let me write this a little more clearly here. So c of xy will be what we get when we integrate this. And remember, we can add an arbitrary function of y, and this equation will still be true. So here g is an arbitrary function of y. I say arbitrary. It's arbitrary in order to have this equation true. But then when we write our second equation, that will tell us something about what g must be. So we also need c sub y to be log x minus 2. And from this formula here, we compute c sub y to be log x plus 0 plus g prime of y. And this must equal log x minus 2. So g prime of y equals minus 2. G of y is just minus 2y. Remember, we could have an arbitrary constant here as well. We just need one representative function, c, to make this work. And thus, we can choose c of xy equals this stuff, y log x plus 3x squared minus 2y. And you can check that this function, c, really works in the sense that c sub x is m and c sub y is n. Then what we do, when we solve this, we integrate. We first divide by the dx here, put it into the standard form, and we integrate both sides, and we get c of xy equals c is our general solution. In this case, that would be y log x plus 3x squared minus 2y equals c. Here, c is arbitrary, an arbitrary constant. And this is an implicit solution, but we can easily solve for y here. If I put the 3x squared on the other side, we'll get here c minus 3x squared. And here I'd have y times the quantity log x minus 2. So I'll just divide by log x minus 2. And we get an explicit formula here for our solution. Again, check that this implicit solution is really a correct solution. You can verify that pretty easily, and that immediately tells us this is the correct explicit formula for our general solution. Before we stop today, let me tell you where we're going with this. We haven't yet looked at examples where m sub y is different from n sub x. So let me just scroll down a bit here. What if we want to solve something like y squared plus x squared dy dx equals 0? Is this exact? Well, this is our m, this is our n, and m sub y is equal to 2y, and n sub x is 2x, and these are not equal. At least they're not equal unless x is equal to y, but we would need them to be equal on some entire rectangular domain in order to have any of this work, to get a solution function that's valid. So what do we do? Well, just like when we were solving first order linear differential equations, and we asked really the exact same question, is it exact? If it is, we can solve it easily. When it was not exact, we looked for what we called an integrating factor. Well, now things will be a little more complicated because here, this is not necessarily a linear equation. In fact, this one certainly isn't, and in general, the other ones we've looked at here are not linear differential equations. And we have functions of x, more complicated functions of x and y going on here because we don't have to have a linear differential equation. But we ask the question, is there still an integrating factor, something we can multiply through the entire equation, left side and right side, and make the left side now exact? That will be the topic of the next video.